Welcome to introduction. I'm Shuntaro Tsubouchi from University of Tokyo. If I'm not mistaken, this is the third time for me to give a talk in European countries. The first was Monday's non-standard analysis seminar. I was invited to by Iona. The second was the workshop in Mitagrefta last year. And this is the third time for me to give a talk. Thank you. I'd like to thank the organizers for inviting me and giving me a good opportunity to talk about my recent progress. However, I have to apologize that my recent work is in preparation, and I'll complete the prepared paper as soon as possible in archive. Okay, let's start. This is the contents of my talk. First, in section 1, I'll introduce the 1p Laplace parabolic problems and some related to topics. Secondly, we introduce the formulation of the 1p Laplace problem, and of course, I'll state the main results. Thirdly, I give some sketches of the proof, and I raise some possible future works, and also I have attached some my acknowledgement. Okay, let's start. In this talk, we consider the 1p Laplace parabolic system of this form. Here the domain is, here the space domain omega is n-dimensional bounded domain with Lipschitz boundary. However, our result is local, so we don't care about the boundary shape. And for the right-hand side, F is in a suitable Lebesgue space, LQ in X, LR in T, so it is the standard Bohner space with the exponent Q and R. These exponents satisfy this inequality. And of course, P is greater than 1 and it is finite. The space dimension N is greater than 2 or equal to 2. And of course, we consider n-dimensional Rn-valued vector problems. My result is the gradient, the spatial gradient or the Jacobian matrix of this U is continuous. Here I denoted, here I use the local I use the abbreviation, I use the notation local because our result is very, very local. However, and also I have to note that spatial gradient, Hölder gradient continuity is still open. This is a pretty difficult problem. I also attach, I'd like to also attach a remark that when P does not exceed this critical value, PC, defined as 2n over n plus 2, we have to require some higher integrability assumption. Okay, this is the main result of my talk. Before stating the main result, I'd like to mention some p-Laplace parabolic regularity or elliptic regularity results. And of course, I'd like to mention some mathematical sources for 1p Laplace problems. For the p-Laplace parabolic problems, as you know, the spatial gradient is in Hölder in some C alpha alpha over 2. So the spatial gradient is indeed Hölder continuous. This was shown by Degenerate and Friedman for the supercritical case. A few generalizations were recently shown by Boccarline, Duzal, Liao, and Sheben. And for the remaining case, Cho in 1993 proved the same regularity result. However, the solution U is required to be in some higher integrability space. So you must satisfy some higher integrability assumptions. For the elliptic cases, there are so many experts. So I have just raised a few researchers. Of course, there are so many experts in p-Laplace regularity theories. And for the 1p Laplace operator, I'd like to note some sources on 1p Laplace operator. The classical one is motion of Bingham fluids. Here, the one Laplace operator reflects complete plasticity, and P equals the two Laplace operator reflects, of course, the viscosity of fluids. So Bingham fluids is a non-Newtonian fluid, which has two different properties: complete plasticity and classical viscosity. Its mathematical analysis at least goes back to the classical monograph by Dubois-Lyon in 1976. Another example is found in crystal surface growth problem with P equals 3. This for the materials I'd like to mention Chpon's paper in 1993. Their fourth order parabolic problems appears. Okay, I'd like to note that the best possible regularity for 1p Laplace problems. When it comes to considering the best possible regularity, it is natural to consider the Facet dual of the energy density. Here, the energy density is E is this one. So the total variation energy plus PD ratio energy. The corresponding Facet dual function is given by this. So this function is in C1 alpha, indeed in C1 alpha with the exponent alpha given by this one. So of course, I have to note that for the one Laplace operator should be treated in the sense of a subgradient or in the sense of a subdifferential. More precisely, the vector field nabla u over the norm of nabla u should be treated as a subgradient vector field. Here, Z is defined as this. Then this u and z satisfy this identity in the point-wise sense. So this conjugate function tells the best possible regularity. This indicates the best possible regularity. However, this C1 alpha regularity is a pretty difficult problem. I have to explain this. So for simplicity, we consider the scalar valued case and no external force. Of course, I'd like to let f equals to 0 for simplicity. So the parabolic equation is formally written by this, with E defined as this standard, this energy density. We formally differentiate this equation by the space variable xj. Then we deduce the linearized problem. Vj is defined as the partial derivative of u. Then, of course, the Hessian matrix appears. However, the main problem is that this matrix is no longer uniformly elliptic. More precisely, we compute the ellipticity ratio, the largest eigenvalue of this Hessian matrix, divided by the smallest one. Then, by straightforward computations, we can compute the ellipticity ratio. But this has a singular term, the norm of nabla u powered by 1 minus p. So this ratio will blow up as a gradient vanishes. So when the exponent here is positive, then this is so-called non-uniformly elliptic problems. There are many excellent problem solvers in Parma University. Of course, there are so many experts here. But I have to note that the circumstance is completely different because the exponent is negative. So for a problem, gradient bound will be easy to prove. But when it comes to the gradient continuity, this will be hard because we will face some non-uniform elliptic structure as the gradient vanishes. So it's hard to prove the gradient continuity across the degenerate region of a gradient. So the flat boundary is hard to deal with in classical analysis. However, we can prove the gradient continuity, C0 regularity of a gradient. Why? This is so we should note that this ratio will blow up as the gradient vanishes, but When W does not degenerate, then it is uniformly elliptic. More precisely, we introduce a truncation parameter delta, and we consider the truncated gradient G delta of du defined as follows. Then this mapping, the claim is that this truncated gradient is indeed Hölder continuous for some Hölder exponent alpha, but this alpha, of course, may depend on delta. However, we can prove the gradient continuity in a rather qualitative way, since as delta tends to 0, this mapping uniformly converges to non-truncated gradient. This method is found in the widely degenerate problem, which the next speaker will talk about. The main difference is that the energy density E is replaced by its potential dual. So E star, we have replaced E by E star. So I prepared the comparison table. The right-hand side is a very degenerate, widely degenerate problems. This also has some non-uniform elliptic structure as a gradient shrinks. However, we can prove the gradient continuity, the continuity of a truncated gradient. This regulatory results has been shown since 2010, starting from Sant'Ambrogio Vespri, then the second one by Colombo Figari, and the recent one by Bogarin, Duzar, Giova, and Passarelli, Napoli in 2022 and 2024 for the parabolic case. The methods therein are based on the classical analysis, including the George truncation and comparisons to heat or harmonic functions. So in this sense, their methods are rather straightforward, and I'm inspired by their work. Then I came to, and indeed I succeeded in showing pseudo regularity. The first one was by Professor Giga and myself in 2022, but the solution is assumed to be convex, and of course it is scalar valued. My recent work removes convexity and of course convexity and scalar valued settings, and indeed I have succeeded in elliptic, and I have succeeded in showing elliptic and parabolic regularity. I almost walk alone, but the works on widely degenerate problems have encouraged me very much. Okay, this is the end of section 1. Now I'd like to introduce some function spaces to give the definition of weak solutions. So we introduce V0, omega V0, shortly V0 as follows. When P is greater than PC, we straightforwardly introduce W1P0. However, when P does not exceed the critical value, we introduce W1, the intersection with L2, so that V0 is continuously embedded in L2. Of course, L2 is continuously embedded in its dual. So, of course, V0 is we introduce a straightforward norm in V0 as follows. Then the function space, the parabolic function space we introduce parabolic function space as follows. So I have to note that the partial derivative of U, time derivative of U, is treated in the sense of functional. This follows from I just follow from the classical monotone operator theory found in JL Lyons. I also note that when P is greater than PC, this embedding is compact, so that X0P space, zero trace space, W zero trace space is compactly embedded in LP L2s. This is so-called Aubin-Lyons lemma. The above one is also, of course, known as Lyons marginal lemma. Okay, this is a definition of weak solutions. Let the external force term F is in this space. So in the functional space, a function U in C0 L2 cap xp is called the weak solution to the LP 1p Laplace parabolic system when if and only if there exists a subgradient vector field L infinity instead of du over the norm of du, such that this inclusion holds almost everywhere for almost every xt. And of course, this identity satisfies in the sense of the functional. This is the definition, my definition. The main result is that as follows. Get the weak solution to 1p Laplace parabolic system. And of course, f is in this space, Lebesgue space. Of course, and these exponents satisfy this identity, which is optimal when it comes to the gradient continuity. Of course, when p does not exceed critical value, we require the higher integrability assumptions. Then the gradient continues. This is my result. I'd like to note that some generalization is also can be discussed. Here, the Euclidean norm is generalized into some quadratic forms, some quadratic norm introduced by some positive definite operator, some positive definite matrix. This is I just follow the recent paper by Bogarin, Duzal, Liao, and Sheven, published in Nonlinear Analysis. Okay, this is the end of the second section. And how many minutes?
13 minutes.
13, okay, okay. Okay, okay, this is the end of section 2, and now I move on to the section 3, final section. The sketch is as follows. First of all, we have to consider some relaxed approximate problem because we cannot carry out, for the original problem, we cannot carry out Bernstein's method. So for this reason, we introduce some approximate problem. Here, we relaxed. So we relax the 1p Laplace operator by some sort of minimal surface operator and some relaxed p-Laplace operator, and also the external force term is suitably relaxed by L infinity function. Here, f epsilon at least weakly converges to f in the weak sense, Lp prime, V0 prime, and also Lr in T and Lq in X. Then the existence theory of this parabolic tissue boundary problem is in the scope of J.L. Lyon's classical monograph. So in the space of U plus X0p, we can solve this. In the space of U plus X0p, we can solve this tissue boundary value problem. When P is greater than PC, we make global approximation. Otherwise, we should appeal to local approximation arguments. This difference is essential when we verify the convergence of a solution. Anyway, we consider this is the setting of approximate problems. Then this is the rough sketch of the proof. We consider the truncated gradient as defined as follows. However, this includes the approximation parameter delta epsilon and the truncation parameter delta. So the difference is that this includes this epsilon. We claim that this truncated gradient is uniformly continuous with respect to epsilon that is not greater than delta over 4. Of course, this gradient continuity estimates may depend on delta. Anyway, we show this header gradient continuity. This continuity, then letting epsilon to 0, we can catch some uniform convergence limit, uniform limit. On the other hand, in step 2, we verify that the gradient, spatial gradient converges to original one in the sense of LPO and therefore almost everywhere. Then these two limits must coincide. So this completes the proof of the gradient continuity, truncated continuity of the truncated gradient, finally letting the data to 0. We complete the proof. So we first mentioned the step 1. So this is a relaxed problem, and the corresponding elliptic ratio is controlled by V epsilon. Here, V epsilon is non-negative, is positive, strictly positive, and therefore it is uniformly elliptic. So we can carry out classical computations, differentiate x alpha, multiply x alpha u epsilon times some composite function psi that is Lipschitz and non-decreasing. Then the resulting identities as follows. Of course, this sounds somewhat complicated, but when psi is equal to 1, then the corresponding composite function is the square function. Most of you will know this. This is so-called Bernstein's method. So for the classical heat equation, the norm of a gradient square satisfies this identity. So the basic computation itself is explained by the classical one. This resulting identity tells us two stories. The first is that this composite function is a sub-solution. The second is we can show some L2 energy estimates of the second order spatial gradient. And also this strategy works even for the vector value case if the energy density has the so-called the Uhlenbeck structure. So in our problem, this energy density is symmetric, and therefore we can deduce this identity. When we treat some external force term, but we can take it easy because this blue highlighted term is positive, so we can carry out standard absorbing arguments. Anyway, so this is the trick of step 1. We let V epsilon be locally bounded for some bound parameter mu. Then so we let these assumptions hold. These assumptions hold. We will take very small ratio mu, and then we consider two possible cases. This kind of division, such divisions by cases are found in Degenerated's monograph and also in Vogel-Induzer and Scheven's work in 2022. However, we have to emphasize that this level set, super level set, includes this delta, so the truncation parameter is included. And this is a key trick. The bound parameter is always assumed to be delta, is always assumed to be greater than delta, since otherwise we consider some strictly truncated gradient, and of course this becomes trivial over the subcylinder. So thanks to this assumption, we can take it easy to carry out some classical arguments. Roughly speaking, we don't care about the delicate region where gradient may vanish. We don't care about some delicate cases thanks to this assumption. So this is completely different from so-called intrinsic scaling methods. But we just appeal to some truncation techniques. This is a trick in showing the Hölder gradient continuity. Next we showed step 2. Firstly, we show u epsilon minus u. The difference is bounded in x0b. So we can this difference is bounded, and therefore we can construct a weak limit. And this is shown by the coercivity structure of the p-Laplace operator. Secondly, we verify the strong convergence of a gradient in LP. This is shown by the strong monotonicity. More precisely, we consider this, we deduce this identity and test u epsilon minus u0 times some scalar valued function that depends on time, that depends on t. Then we can use some weak convergence trick to verify this strong convergence. Here, so roughly speaking, we test u epsilon minus u0 into this identity. The second one and the third one is easy to treat thanks to the weak convergence result. However, we have to treat this pairing. Both of them, so we need, in particular, we have to verify the strong convergence of the difference, u epsilon minus u0. When p is greater than pc, it is easy to show by appealing to the compact embedding. So we can verify some strong convergence of this difference, and we can take it easy. When p does not exceed this critical value, we appeal to some regularity results on u epsilon to verify strong convergence. This is a new result. Okay, this completes step 3. This completes the sketch of the proof. And I have raised some possible future works. The first is very hard, pretty difficult problem because this problem is not uniformly elliptic as a gradient vanishes. There, I have raised some other 3 topics: systems without Uhlenbeck structures, boundary regularity, appealing to boundary regularity of a gradient, and of course, doubly nonlinear problems, doubly nonlinear parabolic problems. And this is the end of my talk. Thank you for kind attention.